To have you here today because we're looking at something truly mind-blowing. We are talking about engineering, but not the kind you can see with the naked eye. We're zooming all the way down to the nanoscale. Think about the last time you upgraded your smartphone or your laptop. You wanted more power, better protection, right? Well, today we're going to look at how scientists do exactly that, but with nanoparticles. We're exploring the super fascinating transition from core shell to core double shell nanoparticles. It's essentially the ultimate microscopic upgrade, and the visual evidence we have to walk through today perfectly maps out how this incredible leap in technology actually happens.
It really begs a fascinating question, doesn't it? How do you upgrade something that's already microscopic? When you're dealing with materials that are just nanometers in size, literally thousands of times smaller than the width of a human hair, how do you iterate on that? How do you engineer a version 2.0 at the tiniest level imaginable? Well, the answer lies in layering. It's all about this incredibly precise, iterative design, literally adding layers of functionality to a central core to dramatically change what that tiny particle can do out in the real world.
All right, here's our roadmap for today. 1. The nanoparticle revolution. 2. Anatomy of core/shell. 3. The double shell upgrade. 4. Head-to-head comparison. And 5. Real-world applications.
Let's dive right into part 1, the nanoparticle revolution, setting the stage.
To truly appreciate this upgrade, we first got to understand the baseline mechanics of why we're tinkering with the structure of these particles in the first place. You might be wondering, why add shells at all? Why not just use a plain, naked nanoparticle? The answer fundamentally boils down to two things: protection and control. You see, a completely exposed core at the nanoscale can be highly reactive, unstable, and honestly, pretty unpredictable. But by engineering an outer layer, a shell, we wrap that core in a customized environment. We're dictating exactly how that particle interacts with the world around it.
Moving right along to part 2, anatomy of core/shell, the standard model. Think of this as the highly capable, highly dependable standard edition of our nanoparticle tech. It's brilliant in its own right and forms the whole foundation of what we're looking at today. Starting on the left side of our visual, we have the standard core shell particle. Notice that distinct, vibrant red core right in the center. And enveloping it completely is a single yellow layer, designated simply as the shell. Kind of reminds you of a layered gobstopper, right? That yellow shell is the crucial barrier sitting directly between the reactive red core and the outside environment. And this brilliantly illustrates the primary function of this standard model. That yellow shell isn't just there for aesthetics, it is a highly engineered outer layer. According to the data, its job is to provide direct surface protection, which inherently leads to reduced defects in the particle overall. By shielding the core, we're literally eliminating the structural flaws that pop up when the core is left exposed.
So, if we look at the core benefits listed under this standard model, we see this solid triad of foundational properties. We've got that surface protection and reduced defects we just talked about, which ultimately culminate in the third point, enhanced stability. Even with just a single shell, we've taken a volatile raw material and turned it into a remarkably stable, dependable tool. I mean, this single shell design is incredibly powerful on its own.
But here is where the story gets really fun. The standard core shell gives us what our source defines as controlled properties. It's reliable, it's predictable, but what if we want more? Let's see how this builds from just having controlled properties to achieving truly enhanced performance. Let's jump into section 3, the double shell upgrade, basically our pro model. If the standard model was a major scientific achievement, this one represents a massive technological leap forward. We're adding an entirely new dimension of engineering here. Now, looking at the right side, the core/double shell nanoparticle. We still have our central red core, but look at what's surrounding it now. Instead of one yellow layer, we have two distinct layers. We've got a green inner shell wrapped tightly around the core, and then an orange outer shell encasing the whole shebang. That green inner shell acts as a completely new layer of microscopic armor right beneath the outer barrier. Notice the crucial shift here to a multifunctional design. By adding that single extra green shell, we aren't just making the armor thicker, we're completely unlocking the ability to design a particle that can do multiple complex jobs simultaneously. For instance, the inner shell could serve one very specific chemical purpose, while the outer shell handles a totally different interaction with the environment. It is the absolute definition of a multifunctional upgrade.
All right, section 4, head-to-head comparison, the ultimate showdown.
It's time to look at the metrics together to really understand the value of that second shell. Seeing them side by side makes the jump in complexity beautifully clear, right? red and yellow on the one hand versus red, green, and orange on the other. But how does that structural change actually translate into performance?
Let's walk through this direct side-by-side breakdown based entirely on our source diagram. Looking at stability, the single shell provides enhanced stability, but the double shell elevates this to higher stability. Moving down to control, the single shell gives us reduced defects, whereas the double shell upgrades that to advanced control. And finally, the overarching focus of the particle shifts dramatically. The single shell is built for controlled properties, but the double shell pushes right into that coveted multifunctional design. Literally every single metric of the standard model gets elevated by the addition of that second shell.
And finally, Section 5, real-world applications, putting them to work.
So why does any of this matter outside of a laboratory? We really need to translate these microscopic, highly engineered features into actual use cases. Our source outlines specific fields where these particles are deployed. Now, both models share some common ground. They are both highly useful for magnetic applications as well as catalytic purposes. However, their unique structures dictate where they truly shine independently. The single-core shell model is specifically highlighted for optical applications. But when we look at the core double shell, optical is gone, and instead it unlocks an entirely new, incredibly complex field, biomedical applications.
So the crucial takeaway here is this: that enhanced performance we just talked about, the higher stability, the advanced control, the multifunctional design made possible by that extra inner green shell, that is the exact key required to make these particles viable for advanced biomedical tasks. Think about it. The human body is a highly reactive, super demanding, and frankly, a terrible place for a naked nanoparticle to hang out. To survive and actually function in there, you absolutely need the microscopic armor and multifunctional capabilities of the double shell upgrade.
It's honestly mind-blowing to see how a single microscopic layer can completely redefine what a piece of technology is capable of. And it leaves us with an incredible thought to ponder as we wrap up today's explainer. If moving from one shell to two shells can shift our capabilities all the way into revolutionary biomedical applications, what on earth could three shells achieve? The iterative possibilities of nanotechnology truly seem endless. Thanks so much for joining me on this microscopic journey. Keep questioning, keep learning, and I'll catch you on the next explainer.